Welcome to section 6.2. Today we want to talk about how to decompose a vector into the sum of two vectors that are orthogonal. So you might be familiar from a physics class with drawing a free body diagram, and we're going to do something like that today. So let's start with a review in the form of true-false. So you might want to pause it and see if you can answer these on your own. Here we go. The matrix definition of dot product of U and V is U dot V is UV transpose. That's false. It should be U transpose V. Number two, in terms of dot product, the length of V is V dot V. Again, that's false. There are two ways to change that. You could square the length, and that is V dot V, or you could write length of V is the square root of V dot V. 3 is true. If U dot U is 1, then the square root of 1 is 1, so this is true. 4 is true. That's the definition of orthogonal. 5 is true because if you dot the 0 vector with any vector, you're going to get 0, so the 0 is orthogonal to all other vectors. 6 takes a moment to calculate in your head the distance between U and V. I did the subtraction correctly. This vector here is U minus V. I'm taking its length. And so I square each component and then add. So 4 plus 4 is 8. So this is indeed true. 7, if U is a vector in Rn, it's orthogonal to a subspace W if U dot W is 0 for all vectors W in Rn. That's false. It has to be 0. This dot product has to be 0 for all vectors W in W. Then it's in W perp. And in fact, here's W perp here. W perp, that's the orthogonal complement, is the set of all x in Rn such that x dot W is 0. It's false because there's a missing piece. This part's true. X dot W has to be 0, but it has to be for all W contained in W. And we learned last time that you don't actually have to check all W, you just have to check a spanning set for W. N9 is a combination of true and false. This piece is true. Rho A perp is null A. This piece is false. Doesn't make sense to take the transpose of a vector space. You can only take the transpose of a matrix. It should read call A perp is null A transpose. Okay, so let's talk about orthogonal and orthonormal sets. A set of vectors is orthogonal if each vector dots to 0 with the other vectors. So we say that they're pairwise orthogonal. And it's orthonormal, which I abbreviate ON, if the set is both orthogonal and all the vectors have length 1. Okay, so here's an example. Show that U is an orthogonal set. So part A, show that U is orthogonal. So what we have to do is show that each vector is orthogonal to the others. So that's going to be 3 checks. U1 dot U2, that should be 0. So if we dot, let's just do this in our heads. 1 minus 1 is 0, so that works. We have to dot U1 and U3. So that would be, that's definitely 0. And then there's one more check, U2 dot U3 is also 0. So that's an orthogonal set. Now you can take any orthogonal set of non-zero vectors and transform it into an orthonormal set by dividing each vector by its length. So for example, if I take this vector, divide it by its length, it's going to have length 1. So let's do that. Our new set will be the first vector, the length of U1 is the square root of 2. So divide by root 2. Negative 1 over root 2 0. The length of the second vector is also root 2. So 1 over root 2, 1 over root 2, 0. And the length of the third vector is already 1, so we can just leave it alone. So now we have an orthonormal set. Each vector is pairwise orthogonal and length 1. Okay, theorem 4. Orthogonal sets of non-zero vectors are linearly independent. That's what you have to come away from for this theorem. Orthogonal, it's in red. Orthogonal sets of non-zero vectors are linearly independent. Non-zero, of course, because whenever you have the zero vector in a set, it makes the set linearly dependent. So I put a proof at the end, and it's worth just pausing for a moment and just going over to that proof and seeing how it works. I hate to just state things without proving them, but I know sometimes the proofs get confusing. I did the proof with just 3 vectors to make it more simple. And I said, show that you've got 3 orthogonal vectors and you want to show they're linearly independent. So what you want to show is that if, by the definition, if a linear combination of those vectors is equal to 0, then that means all the coefficients C1, C2, and C3 have to be 0. And so what you do is you start by just dotting both sides of this equation with U1. And then distribute, and then I say that this equation here implies this one, and I say why? Well, it's because by supposition, u1.u2 is 0 and u1.u3 is 0 because the vectors are orthogonal. So the only guy that lives is C u1.u1, C1, u1.u1. Now I claim that if that's 0, then that must mean C1 is 0, and that's because u1 is not 0, again, by assumption. It's a non-zero vector. So you show C1 is 0. And then you go through and you do the same thing again. You dot this with U2 and dot with U3, and you can show all 3 coefficients have to be 0. All right, so I feel better. I don't know if you feel better or not. Let's go back to theorem 5. Okay, if you've got an orthogonal basis for a subspace W, each vector y in W has a unique representation as follows. And here's a formula, and yes, you do actually have to memorize this, and you're going to use it so much that it won't be too tough to memorize. The corollary, why does the corollary follow from the theorem? Well, if the set is orthonormal, that means the length of each vector of each of the u's is 1. So these denominators here, u1.u1, that's 1. u2.u2, that's 1. And so the formula, the second formula is really just the first formula without those denominators. And that's because all the denominators are 1. So let's put this formula to work. Write y is a linear combination of the orthogonal basis, and we're told it's orthogonal, so we don't have to check. And actually, we already checked on the first page. So here's our set. All right, so I started this out, and I wrote down the formula we're going to use. It's theorem 5 with just 3 u's, u1, u2, and u3. So here we go. We're going to do some dotting. Y dot u1 is 3 minus 7, which is negative 4. u1 dot u1 is 2, and u1, plus y dot u2 is 10, u2 dot u2 is 2, and finally y dot u3 is 4, u3 dot u3 is 1, and so we get negative 2 u1 plus 5 u2 plus 4 u3. So we've written y as a linear combination of u1, u2, and u3. Now, to appreciate what we just did, let's go back to the old days. How would we have done this without theorem 5 if in general we're just given 3 vectors and another vector and said, write this vector as a linear combination of these other vectors? What you would have done is take the augmented matrix u1, u2, u3, augmented with y, and you would have reduced that. And that would have given you the coefficients -2, 5, and 4 that you would use to write y as a linear combination. And so this gives us just a quick formula, and it allows us to save not having to do this. But be careful, you can only use this formula when you have orthogonal vectors. So here's a pause and practice. Write y as a linear combination of these two vectors, and I'm telling you they're orthogonal, so you don't have to check. And write down any formulas you use. And I'm switching up the notation. We're using linear notation here. Okay. So hopefully you did that. Y equals y dot u1, u1 dot u1, u1, plus y dot u2, u2 dot u2, u2. Now you always want to write down the formula you're using. There's two reasons. One, it tells the reader what you're doing. Two, it tells you what you're doing. And three, the more you write down a formula, the more you're going to remember it. So it helps you memorize this formula. Okay, so we want y dot u1. So that's going to be -4 plus 30 is 26. u1 dot u1 is 9 plus 4, which is 13. And then I want y dot u2, which is -4, no, okay, I want -12 minus 40, so -52, put parentheses around that, and then over u2 dot u2, 36 plus 16 is 52, so we get 2u1 minus u2. All right, orthogonal decomposition and projections. So take a look at this vector y and this vector u. I'm claiming that we can write y as the sum of two vectors. One is a vector parallel to u, and the other is a vector orthogonal to u. And so here's y in my picture. I'm saying I can write it as y hat plus z. Sum of those two vectors is y, and they're orthogonal. And I'll just verify that. Why is y hat parallel to u? Well, y hat is twice u. So if you're a multiple of a vector, you're parallel to that vector. And z and y hat are perpendicular. So the check for that is z dot y hat should be 0. And that's 4 minus 4, which is 0. So what I'm going to do on the next page is show you how I got y hat and how I got z, the formulas for those two vectors. Okay, so here are the definitions. If u is in Rn and L is the span of u, the orthogonal projection of y onto L, or you could say onto u, or onto the line spanned by u, doesn't matter, they're all synonymous, is y hat equal so I write projection onto u of y dot u over u dot u, and then you can decompose y into y hat plus z if you let z equal y minus y hat. And then furthermore, one more thing, so there's three things here. This, the decomposition, and the distance. And you have to memorize them all. It's not so bad. The projection of y onto u, y dot u over u dot u, is very similar to theorem 5, except you only have one u. Instead of a bunch of u's, you just have one. Distance is the length of z. So here's my y, here's my L, here's y hat down here. It's the projection of y onto L. That's the part of y that goes in the direction of u. So u is a vector that spans L. So this might be u here. But y hat is the part of y that goes in the direction of u, and z is the part perpendicular to u. And so the length of this dotted line is the length of z, and that's what we say is the distance from Y to L. Okay, so let's do an example. We've got a vector Y, we've got a vector U, and L is the span of U. Find Y hat equal to the projection of Y onto L. So Y hat is Y dot U over U dot U, U. Okay, that's negative 24 plus 4 is negative 20 over U dot U is 10 U. So that's negative 2 U, and U is 3, 1. So that's negative 6, negative 2. So there's my Y hat. Now I want to decompose Y into the sum of two vectors, one parallel to U and one orthogonal to U. So the one parallel to U is the Y hat, and the one orthogonal to U is the Z. So first of all, I need Z. Z is Y minus Y hat. Y is negative 8, 4. And I'm going to subtract the Y hat I just found. And I get negative 2. And then 4 plus 2 is 6. So that's my Z. And then I want to leave my answer in the way it's been requested. Write Y is the sum of two vectors. So Y is Y hat, which is negative 6, negative 2, plus Z, negative 2, 6. So this is my Y hat, and that's my Z. And so that's how I want to leave my answer. Okay, and then there are two checks, which is safety checks. So one, is Y really equal to Y hat plus Z? So add these two vectors together and see if you get the original vector Y. Do you get negative 8, 4? Yes, you do. So that's one safety check. The other safety check is Y hat orthogonal to Z? So is Y hat dot Z equal to 0? So let's just dot. We get 12 minus 12, that's 0, so that's a check. So we did that correctly because this decomposition is unique. All right, and then finally, the distance from Y to L. So the distance is the length of Z, which is the square root of, here's Z up here, that would be 36 plus 4, square root of 40. And I've drawn a picture for you. This is Y. U is, what was U? 3, 1. So U goes into quadrant 1, but this whole dotted line here is L. That's the line spanned by U. If I project Y onto L, I drop a perpendicular like this. So this vector here is the Y hat that we found. And then Z is the vector orthogonal to that. This is my Z. And you can see if I add Y hat to Z, I do get Y. And they are indeed perpendicular. Okay, last topic. And then I'm going to have you do some practice problems for home. And I'm changing up notation. Some I use traditional column vectors. And then in this one, I switch to linear format. Orthogonal matrices. So a matrix is an M by N matrix has orthonormal columns if and only if U transpose times U is the identity. And then if a matrix has orthonormal columns, there are some special things about that matrix which you can read about. And there's an example of an orthonormal matrix that's not square in your text, and you can read about that. I'm not going to go over it. Example in text. I want to jump down here to what an orthogonal matrix is. So if you have a square matrix, square, and it's invertible, it's orthogonal if its transpose is equal to its inverse. Okay, and if that's true, then it has all these nice properties. It preserves lengths, it preserves angles, and then we have another interesting fact here in this box that if U is square with orthonormal columns, then you get an orthogonal matrix. So if you want to check if a matrix is orthogonal, there are two ways you could do it. If it's square with orthonormal columns, you're good to go. Or if its transpose is equal to its inverse, you're good to go. So here's an example. This matrix A is the matrix corresponding to a counterclockwise rotation by pi over 2 radians. So this matrix will just take a vector and it'll rotate it 90 degrees. So let's just see if it's an orthogonal matrix. So let's use the definition. A transpose is equal to, take the rows and turn them into the columns. There's A transpose. And now let's find A inverse and see if it's equal to that. A inverse, I'm going to use the dancing naked bears. First of all, I take 1 over the determinant, and the determinant is 1, so 1 over 1. And then I switch the A and the D, so the zeros switch. And then I make these, the B and the C negative. So that's a 1, and that becomes a negative 1. So indeed, A transpose is equal to A inverse. So that checks. Or I could have, to see if that's an orthogonal matrix, another way to do it is to look at the columns. Let's call them U1 and U2. First of all, U1 and U2 are orthogonal. And the length of U1 is the length of U2 is 1. So it's a square matrix with orthonormal columns, so it's an orthogonal matrix. And indeed, you can see that these properties in Theorem 7, especially property 1 and 2, they're true. When you rotate a vector by 90 degrees, you preserve its length. The length isn't going to change. And if you take two vectors and rotate them both, the angle between those two vectors isn't going to change. It will stay the same. Okay, and that is the end of this section.